In the silent reaches beyond Mars, the James Webb Space Telescope caught something no human eye has ever seen. A collision between two interstellar visitors in a single flash lasting less than 90 seconds. The mysterious traveler from 2017 struck 3I Atlas, a comet speeding through our solar system at nearly 58 kilometers. Webb's infrared sensors flared with energy spikes, dust plumes, and shock-heated gas, proof of an impact across light years of chance. What began as a faint signal became history's first glimpse of cosmic worlds colliding between the stars. The arrival of 3I Atlas began quietly in the data stream of the Atlas Sky Survey on the night of July 14, 2025. A faint moving dot slipped between stars over Hawaii's Haleakala Observatory. Its motion was too fast, its orbit too open. Within 48 hours, orbital solvers confirmed what the astronomical world had barely dared to hope for. A third interstellar object, formally designated 3I Atlas. Its eccentricity of 1.21 placed it beyond capture by the Sun, ensuring it would visit but never stay. Astronomers immediately turned every eye toward it. Unlike its predecessors, 1I Oumuamua in 2017 and 2I Borisov in 2019, Iovae, 3I Atlas displayed an obvious coma, even at 6.4 astronomical units. That early activity startled observers. At that distance, sunlight is weak, and meters most comets remain dormant. Yet 3I Atlas was already shedding gas and dust, glowing faintly against the dark. Its inbound velocity, nearly 58 km/s relative to the Sun, hinted at an origin far from any familiar nursery, perhaps a disrupted planetary system light years away. Its journey had likely lasted millions of years through interstellar cold. Spectroscopy from the Lowell Discovery Telescope and Hubble soon revealed something stranger. The comet's comet coma was dominated by carbon dioxide, CO2, rather than water vapor, a composition opposite to most solar system comets. Ratios showed nearly 8:1 CO2 to H2O, a figure unseen in decades of cometary observation. Such a signature implied formation in a frigid environment, perhaps beyond the CO2 snowline of another star. This was alien ice, preserved since the dawn of another world's formation. Every spectral pixel was a whisper from a different sun. By August 2025, the world's most advanced eye turned its mirror toward it. The James Webb Space Telescope, stationed at L2, 1.5 million kilometers from Earth. Webb could see what ground-based telescopes could not: the infrared glow of molecules in exquisite detail. Astronomers prepared a long exposure using NIRSpec, covering wavelengths from 0.6 to 5.3 microns. They expected subtle data, compositional traces, thermal behavior. But what came through Webb's detectors would defy every assumption about interstellar visitors. As the data streamed down from L2 over the Deep Space Network, analysts noticed something odd. The spectra didn't remain steady. They shifted, brightened, pulsed. At first, it was dismissed as noise or calibration drift. But within minutes, a consistent pattern appeared across multiple instruments. A sudden flash, a plume of high-energy lines, and a change in dust geometry. Impossible coincidences. Something had struck 3I Atlas, and Webb, by sheer chance and precision, had been watching at the exact minute of impact. WST's spectroscopic revelation occurred at 0342 UTC on August 6, 2025. Webb's near-infrared spectrograph, NIRSpec, locked onto 3I Atlas, gathering light for nearly 3,600 seconds. Each photon was a messenger from a traveler between stars. The initial data fit expectations: absorption features of CO2, faint traces of CO, OCS, and a small amount of H2O. But then came a pulse, a spike in brightness concentrated near 4.26 microns, where CO2 vibrational lines dominate. This was not ordinary outgassing. The line profiles broadened suddenly, velocities jumping by over 40 km/h. Dr. Leila Hashimoto, part of the European Space Agency's Comet Physics Group, was among the first to flag the anomaly. Something injected kinetic energy into the coma, her report read. This isn't sublimation, it's impact behavior. Within 12 hours, observatories worldwide were alerted. Ground-based photometry from Mauna Kea confirmed a sharp, asymmetric brightening lasting just under 2 hours. The comet's tail twisted, not aligned with the solar wind as before, but tilted several degrees sunward. It was as if an invisible hammer had struck from the side. Spectral analysis provided the fingerprint. Emission lines of C2, Cn, and OI radicals surged briefly, indicating shock-heated gases. The Doppler components showed both red-shifted and blue-shifted lobes, material moving both toward and away from the observer. That pattern, well known from impact ejecta physics, could only arise from a collision. The energy required matched. A 10-meter projectile traveling at 25 kilometers, small by cosmic standards, yet enough to vaporize thousands of tons of material. For the first time in human history, a telescope had witnessed an interstellar collision in real time. What made this moment extraordinary was not only the detection, but its timing. Webb's continuous infrared coverage allowed a perfect time slice of pre-impact, impact, and post-impact phases. Scientists could now compare chemical states second by second, something impossible before. The event transformed 3I Atlas from a wandering curiosity into an experimental laboratory, one where physics, chemistry, and cosmic history collided together, literally and figuratively. But to understand what truly happened, astronomers needed to go deeper into the physics itself. What happens when an object moving at 58 km/s meets another at cross velocity in the vacuum between worlds? What pressures? What heat? What waves? A vaporization ripple through frozen rock from another star? The next phase of investigation would reveal a process far more violent and more informative than anyone expected. Imagine two travelers in the dark, one small, one vast, meeting by chance after billions of years adrift. The smaller, perhaps 10 metres across, may have been a fragment of primordial dust or a microasteroid from the solar debris field. The larger, Xyle 3I Atlas, spanning roughly 1.2 kilometers, carried layers of ice and dust accumulated since its birth beyond the CO2 frost line of another star. When they met, their relative speed exceeded 30 km/s. The result, an instantaneous release of billions of joules of energy. In such a collision, kinetic energy converts to heat, vaporization, and shock compression. At the impact site, temperatures soared beyond 1500 Kelvin for milliseconds. Local ice vaporized, blasting open subsurface voids, venting long-trapped volatiles. The surface fractured, ejecting grains from micrometers to centimeters in size. Some particles launched at hundreds of meters SS, escaping entirely. Others fell back, settling into the nucleus as fresh, reflective patches. This eruption manifested precisely as Webb's instruments recorded, an abrupt, asymmetric flash. Numerical. Models by the Jet Propulsion Laboratory in 2025 simulated the event. A projectile massing only 46 kilos could excavate a crater 80 meter wide, injecting a cloud of dust expanding over 50 kilometers in minutes. The shock penetrated to depths of tens of meters, exposing pristine interior layers untouched by sunlight for eons. Volatiles like CO, H2O, and complex organics sublimated almost instantly, altering the gas ratios measured by NIRSPEC and MIRI. Every element of the data, the brightening, the new spectral lines, the velocity shifts, matched the impact model. More intriguingly, this impact came as 3I Atlas neared its thermal limit, approaching perihelion near 1.2 astronomical units. The surface was warming, sublimation stresses mounting. The collision may have triggered cascading fractures, accelerating outgassing far beyond natural activity. In essence, it acted as the final spark in a powder keg of internal tension. I-Atlas had become both victim and teacher, a comet unraveling under the gaze of humanity's most powerful eye. What followed was chaos made visible. The plume of ejecta expanded, scattered by sunlight, twisted by the solar wind. Telescopes on Earth and in orbit began capturing new arcs and fans. where none had existed before. It was as if the cosmos had painted a wound across the sky. Yet in that wound lay revelation, the first direct look into the internal anatomy of a traveler from another star. And for the James Webb team, the real work had only just begun.